Okay, so first of all, a little bit introduction. This is technically the definition of the directional derivative, okay? So this is the definition. This means directional derivative, okay? But this is in reality how you calculate it. You take the partial of the, you take the vector, which consists of the partial with respect to x, comma, the partial with respect to y. And you dot product that with a unit vector in the direction. So this is a directional derivative in, so these are directional derivatives in the direction of u, okay? So if you have a vector, if you have a vector that's pointing in the direction that you want, then you first have to normalize that by dividing by its length, so that you get a unit vector. So this has to be unit vector. This has to be a unit vector. It can't have. It has to have length 1 and pointing in the direction that you want. Okay, so that's the directional derivative. And this is in the context of a surface, okay? So F, so the F has to do with a surface. And so basically, if you take F of x, y, in this context, it's like z equals F of x, y, okay? So that's your surface. That's a surface in 3 dimensions. Then, and so as a surface, you can kind of imagine that you're out hiking in the mountains. Okay, let's say you're hiking up to Lehigh Falls or whatever other good place there is to hike around here. As you're going around, the terrain underneath you changes, and so suppose you're walking on the side of a mountain. So let's suppose that we're going directly kind of into the board. So maybe this is you right here. Okay, so you're walking along the side of a mountain. Okay, now there's actually, according to, if you look down, there's 360 degrees of directions that you can move, right? You can go that way, you can go that way, you can go forward or backwards, right? If you go this way, you're going up. If you go this way, you're going down. Okay, so if this is the surface that we're talking about right here, then the directional derivative this way would be positive, and the directional derivative going this way would be negative. So the directional derivative would be whichever direction that you move, that's what's going to happen. That's what's going to happen to the surface if the surface is going, and the rate at which the surface is going to be decreasing. Okay. Now, if you go forward or backwards, your derivative could be 0, right? If you're walking along the side of the mountain. And the steeper this is, the larger this is going to be. Okay. So that's kind of a little introduction to what that is, and then it's regards to a surface. Okay, now the next thing is the gradient vector, and that's what this is right here, which is related. It's kind of related because you're taking partials of this. You're forming a vector with the partials of x, y, and z. Okay, and this right here is going to be. This is where you have a slightly different context. So you have f of x, y, z equals c. This is the context there. This is also a surface, but it's in this form here. So basically, it's like if you took this to this side of the equation, then you'd have, and then you formed a new function out of these, which is in x and y and z. And this vector is perpendicular to the surface. Okay, and these are equations of plane right here. The equation of the plane that is tangent to the surface. Those are those two right there. And I think we've gone over those before. Okay, so let's, with that in mind, let's go ahead and do some calculations, or let's take a look at this right here. Okay, so number one, level curves for barometric pressure are shown for 6 a.m. on a day in November. A deep low with pressure 972 is moving over northeast Iowa. The distance along the red line from Kearney to Sioux City is 300 kilometers. So from here to here, it's 300 kilometers. Estimate the value of the directional derivative of the pressure function at Kearney in the direction of Sioux City. Okay, so the directional derivative right here in this direction. That's what you're estimating, that vector there. So, so let's see, this right, Kearney, you're at 1,000, right? So this is 1,000, is the barometric pressure in millibars. And what's the pressure here at this one? That's 976, right? So if you take the directional derivative, is always changing the dependent variable, which is going to be 976 minus 1,000. So you take the end point minus the beginning point. So that's 976 minus 1,000. And then you divide by the distance, which is 300 kilometers, right? Between them. Okay, and if you do that, then let's see, what do you get? Anybody get an answer? Negative 0.08.
Yes, that's what I got.
And it's going to be this one here, okay? Because the numerator is millibars and the denominator is kilometers, right? This is kilometers. Okay, great. So that's this one. Okay, number two, find the directional derivative of this equals cosine xy at the point 0, 1 in the direction indicated by the angle pi/6. Okay, so what we need to do, first of all, we can find fx and fy, and we form a vector, right? So fx would be what? The derivative partial with respect to x would be negative y sine xy. And the partial with respect to y would be negative x sine of xy. Yes. Yes, perfect. Okay. And then we can plug in the point 0, 1. Wait a minute. What? Just a second. 0. Wait, that doesn't make sense.
A sine of 0, it's gonna be 0.
Oh wait, I copied it down wrong. Okay, I made a mistake in copying this down. There should be a y right here. So good. So partial with respect to x is going to be, oh, it's still going to be the same thing.
But is it gonna be squared?
Y squared. Yeah, the y is going to be squared. Okay, and then the partial of this respect to y is going to be cosine of xy minus xy sine of xy. Okay, good. Now, at this point right here, what you're going to do is you're going to set x equal to 0 and y equal to 1. And that's going to make that all 0. And this will be 1, because this cosine of 0 is 1, and then that's 0. So it's going to be 0, 1. Okay, that's going to be this part here. Okay, meanwhile, over here, this angle here, pi over 6, that is this direction here. Okay, so pi over 6 means that we have a triangle that is 1, 2, root 3. So a vector in that direction will be, we'll call it v. A vector v in that direction would be going to the right by root 3 and up by 1, right? But the magnitude of v is 2, right? So u is going to be root 3 over 2 and then 1 over 2. So the directional derivative is going to be, okay, here's the formula. Dot product with u, with the vector u. Okay, which in this case is going to be the dot product of 0, 1 with this one. And that dot product is, okay, 0 times that plus 1 times a half. So it's just going to be 1/2. Okay, so you guys see that?
So we're kind of like using the